Alright, our purpose here is to study some functions that are not polynomials. They're not just curving smoothly around the set of axes. They've got different characteristics than the ones we've looked at so far. And none of the rules have changed about what's going to cause relative min and max and inflection points. All that stuff's still the same. We just have some different unique features. So let's just start. Our goal is to sketch this graph using some calculus. And you might already know what this graph looks like, but let's just assume that we need these calculus features to discover what it looks like. So this always starts with the derivative. If the function is x to the 1/3, then the first derivative is 1/3 x to the negative 2/3, or 1 over 3x to the 2/3. Now, what you should notice is that the denominator has an x in it. This derivative is never equal to 0, which means our graph will never have a horizontal tangent line. The only way for a fraction to equal 0 is for the top to equal 0, and the top of this fraction is 1. However, this thing is undefined at x equals 0. So that means our function is not differentiable at x equals 0. So something's going on there. The function is defined at x equals 0. But the derivative is not. So there's a couple options that can be going on there. An undefined derivative could be a sharp point, but it also could be a vertical tangent line. So we need to kind of see what's going on in this case. The point in question, by the way, is 0, 0, where the function is defined, but the derivative is not. So let's just look and see what we can discover about this point 0. We can do test points. Any point, I'm going to start with -1, and I'm going to put in +1 because our critical value is 0, the value that makes the derivative undefined. If I sub -1 into this derivative, then I'm doing -1 to the 2/3. Now it's -1 squared and then cube rooted. Whether you cube root it and then square it, or square it and then cube root it, either way it turns into +1. So this becomes +1/3. And again, the only thing that matters is that it's positive, which means my function is increasing. When I plug in 1, the same thing's going to happen. It's going to be positive. This is what f prime of x. And I know that I called it y prime in the question, but I like f prime better at this point, so I've changed. So this tells me that f of x is increasing, and it's also increasing after the point 0. Okay, so it increases everywhere. That's possible. That happens in a lot of functions. So let's check concavity. We don't have any max, relative min. A sharp point usually is one of those two. I don't guess it always has to be, but it usually is, and this is not one of those. So let's check concavity and check y double prime. Okay, so if y prime is 1/3 x to the negative 2/3, then y double prime would be -2/9 x to the negative 5/3. Okay, I'm just working from here and taking an additional derivative. Dropping the negative 2/3 down, it becomes -2/9. I decrease it by 1 and I get negative 5/3. This can also be written as -2 over 9x to the 5/3. Okay, so 0 again is the point in question, possible inflection point at 0. I can still check -1 and +1, except this time I'm plugging them into the second derivative and seeing what I get. So if I plug in -1, the difference here is that this 5 is odd, whereas this 2 was even. So if I plug in -1, I get -1 to the 5th is negative, cube root's negative, but I have a -2 on top, so overall f double prime of x is positive, which tells me my function's concave up, and f double prime of 1 is negative, which tells me my function is concave down. So I have an inflection point at 0, 0. So 0, 0 was the one point we were worried about. It turned out not to be an extreme value, min or max, but it did turn out to be an inflection point. So what does a function look like that always increases, that has an undefined derivative at 0, and has an inflection point at 0, 0? Here you go. It looks like this. And again, x to the 1/3 is the cube root of x. You might have remembered what it looked like. But here was that main point we were looking at. We have concave up changing over to concave down, which makes this inflection. But this thing was increasing, always on its way up. So this is what we know. Let's move on to another one. All right, so it looks close, but this time it's x to the 2/3. Try to do that same process and see if you can guess, without graphing it on a calculator, what does x to the 2/3 look like according to the first and second derivatives. I'm going to pause and fill that stuff in. I encourage you to pause and work it out and come back for the answer. Okay, so here's where I stand right now. I have the first derivative here. It's undefined at 0, which means a possible critical point is happening at 0. Actually, 0 is a critical value. A possible min or max is happening there. So to check and see for increasing, decreasing, I plug test points into the derivative, into here. When I plug in a -1, I get a negative value, which means my function decreases. Positive, increasing after 0. So a change from decreasing to increasing creates a relative minimum. Using the second derivative, I get that same point, kind of like it was with x to the 1/3, except this time it's concave down everywhere. So 0, 0 is not an inflection point. So before we look at the official graph, let's just kind of sketch what we know. I know this graph goes through 0, 0. I know it needs to be decreasing and concave down before it gets to 0. All right, so it always decreases and it's always bowl-shaped down. About the only way that can look is this. Now we have an undefined derivative at 0, 0, and this is a sharp point. It's a relative minimum, but it's also a sharp point. After 0, 0, I need to increase but still be concave down. That looks like this. Okay, an undefined derivative to increase being concave down to an undefined derivative, then decrease, then increase after that. This is about the only way it can look, and next slide will show us the official picture. All right, and here's x to the 2/3. It's similar to the cube root graph, except this part down here has been flipped up positive because the squared portion of the 2/3 exponent makes everything positive, and that's what we analyzed in the last slide. Okay, let's finish up with this graph. I'm going to try to fit it on this slide and graph it also in this slide. And really the point of this one, not only to practice our new skills, is to don't forget your old skills. You learned about rational exponents in Algebra 2 and again in pre-calc. Vertical asymptotes happen when the bottom is 0 and the top is not 0. 2 and -2 both are values that make the denominator 0, and 1 over 0 is sort of like infinity, and infinity in graphing terms is basically a vertical asymptote. The degree of the denominator is bigger. It's squared, whereas the top is linear. That means 0 is the horizontal asymptote. So all the things that we used to know about rational function graphs still apply. We just are able to discuss them in a different context. How about x-intercepts? This thing never has an x-intercept because in order for this fraction to equal 0, the top would need to be 0, and that doesn't happen. Y-intercepts are where x is 0. If I let this x be a 0 right here, then I get -1/4. So I can add to my graph a y-intercept of negative 1/4, which lives right about there. And if I know it has no x-intercepts, that kind of tells me what's going on. But I want to use concavity and increasing, decreasing, and that sort of stuff to see if I can figure out with calculus some of the things that I used to know how to do without. So let's start with the derivative. F prime is negative 1 times x squared minus 4 to the negative 2, don't forget your chain rule, times 2x. And I can rewrite this as, let's see, negative 2x over x squared minus 4 quantity squared. Now, changes can happen where this thing is 0 or undefined. Technically, plus and minus 2 are not going to be critical points because the function is not defined there, and it has to be defined in order to be a critical point. But I have a possible critical point at 0, and I also need to add to my test values, to my checkpoints, I need to add plus and minus 2, because even if it's not a critical point, it still could represent a change in increasing to decreasing. So on my number line, which I don't always write this, but these have negative infinity on either side, I want to check negative 2, 0, and positive 2 in the first derivative, and that's going to tell me things about the function. So how about, I don't know, negative 3, negative 1, 1, and 3. Those will work. At negative 3, this is going into the first derivative. Think about this derivative. The bottom is always positive, right, because it's squared. And the top will change to positive or negative depending on what values we sub in. So f prime of x at negative 3. If I put a negative 3 on top, I get a positive 6 on top. So I get positive over positive, which is positive, which tells me my function is increasing. If I plug in negative 1 on top, I get positive. Bottom's always positive, still increasing. If I plug in positive 1 right here, I get negative 2 on top, which tells me it's negative and decreasing. And it stays negative and decreasing. So I wasn't looking for min and maxes at negative 2 and 2 because those are these asymptotes. Min and maxes are not going to happen there. But I do have, and it stayed increasing and decreasing anyway. What I do have here is a change from increasing to decreasing, which represents a max. And let me include relative max at the point 0. And using our old stuff, we already figured out that that's 0, negative 1/4. So we've just kind of confirmed the point that we knew, and we've confirmed that it's a relative max. So what I know is my function increases everywhere to the left of the asymptotes. It increases, then decreases up to this relative max. I'm going to confirm this with the concavity in just a minute, but can't we pretty much determine what's going on in here in the middle? Is like an upside down U. Let's get to the concavity also, but I'm just anxious to get this graph drawn. Let's check out the second derivative. It's going to be a little bit more labor involved in this one, but we can handle it. F double prime. Actually, we'll, for the sake of time in this video, see if you can take the second derivative and determine where this function is concave up and concave down, and come back for the answer. Okay, now I'm about halfway through that process. I chose to use the quotient rule on this first derivative to get my second derivative. What happened when I did that is each term had an x squared minus 4 in it. There were 2 of them here, so I crossed it out and just left the 1. There was 1 in my second part, so I crossed it out completely, and there were 4 in the bottom, so I crossed them out and made it cubed. That green 3 is a cubed. So then to get to this next line, I distributed the negative 2 backwards, and then over here I just needed to multiply negative 2x times 2 times 2x, and that negative sign gave me a plus 8 squared, 8x squared. So overall I get 6x squared plus 8 over x squared minus 4 quantity cubed. All right. And so what this tells me, this is never 0. The only two places this is undefined are at the two asymptotes. So those are possible changes in concavity, but it's never 0. So though I don't have to check any other places. This denominator or this numerator can never be 0. So basically I need a test point from the left, the right, and the middle into the second derivative to see what I get. And I'm going to kind of, again, to save us some time, cut to the chase. This thing needs to be increasing over on the left-hand portion. So if it's going to approach these asymptotes and it's going to be increasing, let's just agree that it has to be up here as opposed to down here, which wouldn't make any sense because this function is decreasing. Now technically, to confirm with concavity, if I plug a test value like -4 into the second derivative, f double prime of -4 is going to be positive, which gives me a concave up. It's always concave down in the middle, so at -1 or 0 or 1, I'm going to get a negative second derivative, which tells me that this portion here is concave down. And we've already talked about the increasing, decreasing portion. We're just confirming what we already know. And then if you check the right side, if I put in a number like +4, I'm going to get another positive, or I'm going to get another concave up. And it has to be decreasing over there. This is an even function, so it has y-axis symmetry anyway, because the only x in it is x squared. So I kind of rushed through that last part a little bit, but again, the purpose of this one is just to do some of our new techniques with a little bit more complicated function that we already knew a lot about, just to confirm that they work with a picture that we're familiar with. And last thing, here's that official picture so we can double check what we did.